So let's briefly recap what we learned in previous class. So what we learned in previous class is homogeneous coordinate to address some discrepancy between captured 2D image and real 3D world. And obvious example is vanishing point. So the two parallel lines in 3D world will not intersect with each other, but in 2D space, as you can see, they are getting closer and closer, and maybe at some infinite point, they could intersect with each other. But that is definite discrepancy between captured 2D image and real 3D world. So that is the reason why we are trying to introduce homogeneous coordinates, which is simply just adding one more scalar. So we introduce additional scalar to represent. We use 3 scalars to represent 2D points. So by introducing this W, we can normalize them to x, y, 1, so that this is just a homogeneous coordinate. And this shows some visualization, relationship between homogeneous, inhomogeneous, augmented, and homogeneous vector. Augmented vector just a some specific example of homogeneous coordinate where W is equals to 1. And we define some singularity, like line at infinity, which passes all the ideal points, where ideal point means W equals to 0. And we got some high school math, and it turns out that the two parallel lines, as you can see here, x equals to 1, x equals to 2, they do not intersect with each other in 3D space, but according to our homogeneous space, in our homogeneous space, they could intersect with each other at vanishing point. Vanishing point means W equals to 0. This is singularity in the homogeneous coordinates. And here we define this, what is this? Line at infinity, a line at infinity. They are intersecting with each other, line at infinity, and some specific example of W equals to 0, some intersecting point of these two lines intersecting with each other by making dot product between them. So that is what we learned in previous class, and we can just simply extend this concept to 3D space, just so that we represent 3D coordinate with 4 scalars, x, y, z, and w, and all the remaining things are the same. And now today we will start from geometric transformation. But any question do you have over the homogeneous coordinate? If anything is unclear, or it's okay to go proceed to the transformation. So these are just so we are going to study 2D geometric transformation in image processing, just some basic concept. And this is actually widely used in these days for augmented data sets. So we have, let's say we have some images, bunch of images, but always we are hungry with data. So let's say we have image 1, 2, 3, 4. But if we train some large system, if we train some neural network, we'd like to augment the training set by applying such kind of geometric transformation. Of course, we can introduce texture transformation, like adding some noise in the RGB space, but geometric transformation for augmenting data set is also widely used. So we often rotate or translate or scaling, apply some scale to the training set so that we can literally augment the training set. So anyway, what we are trying to do is study such kind of various geometric transformation in image space, in 2D space. And this shows all the transformations that we are going to study: translation, Euclidean, similarity, affine, and projective. So let's see one by one. The translation is very simple, just adding some 2D vector. So we like to just move the square, move the square to some different position. That's all. So there is only two. The DOF means degree of freedom. What we can control is just the 2 variable, position of center of x and position of center y. That is all we can control with this translation transformation. In vector form, we can simply write this, and in matrix form, we can introduce some identity matrix and some row vector, and then we can use translation vector so that we can represent this translation transformation with matrix multiplication as well. It's clear, right? Just moving some square to the different position. All the remaining things are the same. And Euclidean. Euclidean means combination of 2D translation and 2D rotation. So that means we have 3 degree of freedom. In translation, we had 2 degree of freedom, x position and y position of center. But in 2D rotation only has 1 degree of freedom, right? We can just, so this is rotation axis, and this is rotation axis. So you just try to rotate this pencil in this direction. Only 1 degree of freedom, only one scholar can represent 2D rotation. So that by combining 2 degree of freedom from 2D translation and 1 degree of freedom from 2D rotation, we got 3 degree of freedom for the Euclidean transformation. In vector form, we can write like this, Rx plus t. And in matrix form, we can replace. So in previous translation, we had ID vector, identity matrix, at the upper left of the transformation matrix. But in Euclidean, we are going to replace the identity matrix with the rotation matrix. I guess you at least already heard what is rotation matrix. Rotation matrix definition is some matrix that satisfying these 2 properties. The first one is multiplication between itself and transformation is transpose is identity matrix. That means inverse is transpose of matrix. That is the first characteristic of the rotation matrix. And the second one is determinant is 1. So these are 2 characteristics of rotation matrix. And then Euclidean transformation preserve Euclidean distances. So there are 4 points, right? Of course, there are many points, but let's say we have 4 points. Distance between 4 points are preserved after translation, after rotation, because all the points are applied with the same transformation. So the distance between each point remains the same after applying Euclidean transformation. And similarity, now so far we introduced translation and combination of translation and rotation. And then we are going to introduce scale as well. So here, this is a combination of translation, rotation, and scale. So there are 4 degree of freedom. 2 from 2D translation, 1 from scale, and 1 from 2D rotation. Scale is just a, adjusting size of the some data. Like if we multiply, this is a mathematical form, vector form. If s is larger than 1, then we'd like to make the square larger than the original size. If the s is smaller than 1, of course it should be positive. Then we'd like to make the original data smaller. In matrix form, we can just write like this. R is still rotation matrix. That means R is not arbitrarily matrix. R is still rotation matrix. That is the reason why we got 1 degree of freedom for this 2D rotation. And S is arbitrary scale factor. And similarity transform preserve angle between lines. So in Euclidean distance between points are preserved. We just apply global translation, global rotation. But in scale, distance could change according to the scale. So distance between points could change, but angle between lines is still preserved. And Euclidean transformation, this is actually widely used in 3D as well. And this is often called rigid transformation. Rigid transformation. Applying only 3D translation and 3D rotation. That in 3D space, people say rigid transformation more often than Euclidean transformation. And affine transformation. So far, for the Euclidean and similarity, the upper left matrix was rotation matrix, right? Well, we got this rotation matrix upper left, and also here, upper left rotation matrix, which satisfy these 2 characteristics. Inverse should be transpose, and determinant should be 1. But in affine transformation, finally, we are not restricted with the rotation matrix. A can be any arbitrarily matrix. So A, now from affine matrix, affine transformation, the upper left matrix, there is no constraint for the upper left matrix. in the translation, upper left was identity, just a constant. Euclidean rotation matrix, similarity, scaled rotation matrix. But affine transformation, now it's just arbitrarily 2 by 2 matrix. And the remaining things are the same. Just so the only difference from Euclidean similarity is that we replace rotation matrix with the arbitrary 2 by 2 matrix. That is all. As you can see, the result seems quite different from the Euclidean transformation and similarity transformation, because the Euclidean distance and similarity transformation, we used rotation matrix, but now we use any arbitrary matrix so that it can, it might change angle between lines, it might change distance between lines. So what is preserved now? Parallel lines. Now parallel lines remain parallel under affine transformation. So these two lines were parallel in the original space. After transforming this space to the with the affine transformation matrix, these two lines still are parallel, and this one also same. This one still also parallel. As you can see, the angle between two lines or distance between 2 points could change with affine transformation matrix. And projective. Projective is now about some the most complicated one, and it has 8 degree freedom. 8 degree freedom. And this one is what we are going to study from now, actually. This explains this, relationship between real 3D world and 2D space, and it can, with this projective transformation, we can explain vanishing point, the vanishing point that I introduced in the first of this slide. Homography, in other words, homography, projective homography, and here we use H, and so here A was 2 by 2 matrix, arbitrary 2 by 2 matrix, but the remaining things, they are, the last row vector should be 1, 1, 0, 0, 1, and translation, and the last one should be 1. That was constraint of affine transformation matrix. But now, H, any arbitrarily homogeneous 3 by 3 matrix, specific up to scale. So that means this one should be maybe 1, but this one, 0, 0, should be any arbitrary numbers. So that is difference between affine transformation matrix and projective transformation matrix. And that is the reason why we got 2 additional degree of freedom compared to affine transformation matrix. So we have 8 degree of freedom, and here we have 6 degree of freedom. By replacing this 0, 0 to something like AB, then we got another 2 additional degree of freedom by replacing 0, 0 to any numbers AB. So that the final matrix should be for homogeneous, we have A, T, A, B, 1. That is, A is 2 by 2 matrix. And this is column vector of the size of the 2. So specific up to scale. And projective transformation preserve straight line. So now translation, the distance was preserved, Euclidean distance was preserved, similarity, angle was preserved, affine, parallel was preserved, but now projective. Now parallel is not preserved, and that is, we are familiar with this, right? In 3D space, 2 parallel lines was parallel, but after some transformation to 2D space, these parallel lines in 3D space becomes non-parallel in 2D space. This is 3. And now finally we can explain this transformation with projective transformation. Now in projective transformation, parallel lines are not preserved. Although 2 lines are parallel in original space, after applying this projective transformation, parallel lines are no longer parallel in after transformation. So that all these things, translation, Euclidean, similarity, affine, cannot explain such kind of vanishing point, discrepancy between 3D and 2D, such kind of stuff. But now with this projective transformation, we can now explain discrepancy between 3D and 2D. In 3D, parallel lines, they do not intersect with each other, but in 2D space, they could meet in vanishing points, and that can be explained with projective transformation. And mathematical definition of projective transformation is just a arbitrarily 3x3 matrix where the right bottom element should be is 1. So the projective transformation preserve only straight lines. So this is straight line, right? Straight line is still straight line. This straight line does not become like a curved line. This is not happening. According to some transformation, maybe a straight line could be changed to curved line, but in projective transformation now, straight line is still preserved to the straight lines, but all the other things could change. Distance between 2 points, angle between 2 lines, parallelism between 2 lines, they could change. Only straight line is preserved after applying projective transformation. And 2D transformation on covectors. So the covector means I. So I is like where is I? This coefficient for this one m or this one I. So coefficient of some linear equation or plane equation. This vector is called covector. And applying 2D transformation on covector. For 2D I, for 3D m, like a coefficient of linear equation or plane equation. Considering any perspective 2D transformation, we just learned perspective transformation in previous slide, right? H. The transform 2D line equation is given by, so let's say we have any transformation. So H is arbitrarily, X and X prime are also arbitrarily points. The transform 2D line equation given by this one. So originally we have X prime and I prime. This was covector of X prime. And then we just replace this with this equation where X prime is come from multiplication of projective matrix and some point, some X point. And then we can just do simple math to change this to this form where we can redefine this as another covector. So now then we have this equation. Therefore, we have I prime equals to H minus transpose I. But the action of projective transformation of covector, such as 2D line I or 3D normal, can be represented by the transpose inverse of the matrix. So how can we interpret this? How can we intuitively interpret this? So let's say these points are, this X prime and X, H is used to transform this X to X prime, right? But X prime is on the line I prime and X is on the line I, so that, after transformation, they still need to underline so that we, need to cancel this H by applying H minus transpose. That is how we can intuitively interpret this result. And let's summarize what we learned in 2D transformation. Translation, so as I said, Euclidean transformation, especially in particular in 3D space, what people call is rigid transformation. Of course, Euclidean this transformation you can call this, but what people more often call is rigid transformation. And it preserves orientation. After applying rotation, now orientation is not preserved, length is preserved. After similarity, we apply scale so that distance is not preserved, just angle is preserved. And affine transformation, the bottom left are 0, 0, right? A, T, 1, that is affine transformation, right? So with this affine transformation, we preserve parallelism. And finally, projective transformation, only straight lines. This AB becomes any arbitrary number in projective transformation. And transformation forms nested set of groups closed under composition inverse and interpreted as restricted 3x3 matrices operating on 2D homogeneous coordinate. And transformation preserve property below, similarity. For the similarity, similarity, angle, parallelism, straight lines. This just says, superset. Translation, it preserves all the things. Rigid transformation preserve length, angle, parallelism, straight line. You can understand this. So anyway, this is a summary of 2D transformation. And we can extend this to 3D. It'll be a little bit more complicated, but similar thing is happening in 3D space as well. Translation, we'd like to change the center position of this object to this some position so that it preserves all the things, length, angle, parallelism, straight line, orientation, all the things are preserved. Rigid transformation, as we rotate this, now orientation is changed, but the length, angle, parallelism, straight line preserved. And scale, similarity, we additionally apply scale, which we make it larger. So the distance is not preserved, but the angle, parallelism, straight lines are preserved. So we can, so 3D, in 3D space, the similar thing is happening. And then back in the day, the representative application of this transformation is panorama stitching, image stitching, panorama stitching. We in our mobile phone we have panorama mode, right? We can capture very, very high field of view data with this by simply moving our camera, right? So how that's happening? So we capture the mobile phone capture images. As we change the rotation and translation of our camera, then we have multiple images captured from a time sequence, and then we can just stitch. Stitch means, you can see, this is from time step 1, this is from time step 2. There should be overlap, right? There should be overlap. Maybe you can see this part is overlap, intersection of these 2 time steps. They find some correspondence between these 2 images from different time steps using some off-the-shelf, like SIFT. Remember SIFT? I introduced SIFT in computer vision history. SIFT was widely used for finding some correspondence between 2 images back in the day. And then once we got correspondence, for example, this position is like this position, or this position is this position. We have some correspondence between these 2 or some many points. From this correspondence with many points, of course there should be noise outliers, so we need to cancel some outliers. But anyway, if we get some reliable correspondence between 2 images, we get a projective transformation matrix, which can explain relationship between these multiple points and multiple points. And then now we have, so the image 1 is, so our goal is finding projective transformation matrix, which can explain correspondence between 2 images, which has some overlap. And then we transform this image T2 to T1 space by applying our optimized homography matrix, so that image is converted to this space, and then we make some blending to make a seam artifact less and other things. But this is basic principle of image stitching or panorama stitching. Find some correspondence with off-the-shelf algorithm, and then based on the correspondence we calculate homogeneous projective matrix, and then we transform images from different time step to the target time step by applying the optimized homography matrix. Okay, so we studied some basic primitives and transformation, geometric transformation, and anything is unclear? I might speak too fast. That is my personal habit. I might speak too fast. So if you feel this is too fast, feel free to stop me. I'm trying to speak actually slowly, but if you feel still this is too fast, feel free to ask any question or feel free to interrupt me. And it's okay. Let's go to geometric image transformation. So as I said, so we are living in 3D world, but what we see is always 2D projection of the 3D world. So you might be confused what is exactly difference between 3D and 2D, but what we see is always 2D. You can understand like this. What we see through our eyes, what we see through our mobile phone, what we see through our display, what we see in 3D, which is called 3D games, what we see through which is called 3D movie, all the things are 2D. All the things are 2D, but where they originate from is 3D space. What we see is always rendering or projection of such kind of original 3D data. And then where they originate from is 3D data. So we are living in 3D world. These are some 3D world. We always see is 2D image. We always see 2D image. And there's no depth dimension, only height and width dimensions. 3D games, as I said, when I was a student, I was really confused. I mean, the video games or movies are called 3D game or 3D movie, but professor said what we see is 2D, but there's a discrepancy. They advertise their games or movies are 3D, but what we are seeing is 2D. Why there's a discrepancy? Because the original data, where they originate from is 3D data, 3D game or 3D movie. But anyway, what we always see is 2D data. That is difference. So both are correct. What we see is 2D, but actually they were 3D. These are really a little bit confusing, but you can understand where they originate from is 3D. And 3D games and 3D movie have their 3D representation, but they render the 3D representation to 2D screen space. That is what we see. And so this is some picture. Back in the day, before camera is invented, there was no way to capture this 3D world in 2D space. We often want to draw a picture. Capture this moment, right? But before camera is invented, there was no way. So that is the reason why people, back in the day, draw some pictures, like drawing some scene, drawing some object, drawing people. And now we have camera so that we can easily capture this scene, this object, this people with camera. So camera is a machine that capturing 3D world in the 2D space. This is also the same. It's like a function, taking 3D world and output 2D space. And so let's briefly study origins of pinhole camera. So pinhole camera is a very simple but effective model of camera, modern camera, model of modern camera. It's based on some very long history. Based on our eyes or some very early machine of camera and photographic camera invented in 1816. And this is some camera obscura, 4th century BC. And to be honest, I actually do not know this machine. Origin of the pinhole camera, and this shows some visualization of pinhole camera. So there are two words, pinhole and camera. So camera we know, right? So machine that capture real 3D world in the 2D space. That is the machine that we call camera. And what is pinhole? Pinhole is here. There's a very small black hole, right? Here. There's a very small hole, and this is called pinhole. In physical camera model, this is 3D world, actual 3D world, and then there is a ray from, rays from light source. There is a sun, and it hits the object, and then the reflected light comes to the pinhole of the camera, and then so that pinhole is just some very small hole that collects all the lights into the camera. And here we have image plane. As you can see, in physical pinhole camera, image is projected upside down onto the image plane, which is located behind the focal point. That is the very brief approximation, visualization of camera. We have original 3D world, and then lights reflected from light source is collected to the pinhole, and then it goes through the pinhole, and then the image plane is upside down. So when modeling perspective projection, we assume image plane in front. So this is physical camera model, actual camera model. But we need to always concerned about this kind of upside down problem. So it is a little bit annoying, right? So in mathematical camera model, from now on, mathematical camera model or any computer vision, computer graphics, anything, we are now going to say image plane in front, this one. So actual image plane is behind the focal point, but there's no difference. We always multiply -1, then we can always make it upside. Prevent it from upside down. That becomes much easier. So from mathematical camera model, we say image plane is in front of focal point by just multiplying -1 to the y-axis and then translating it to x-axis in a symmetric way. Both models are equivalent. There is no difference. There is no difference with appropriate change of image coordinates. So from now on, we will use this coordinate system. There are camera coordinate system, focal points, image plane, some complicated things, and we will study this one by one. So from this slide, we can know that what is pinhole? Pinhole is a very small hole, exists in the physical camera model to collect light reflected from object. And then in physical camera model, image plane is behind the focal point, but in mathematical camera model, we'd like to put in front of the focal point to make the calculation easier. And so of course, there could be several ways to project 3D world to 2D space. Actually, all the projection follows perspective projection. Always perspective projection. Perspective projection is the only right thing, only correct thing. But we can approximate such kind of perspective projection to mathematically easier one, like orthographic projection. So here, orthographic projection, from its name, we can know that there is some orthogonal, right? There is some 90-degree stuff. 90-degree stuff is from here, right? 90-degree. So, in our real world, if object becomes far and far from our camera, it becomes smaller and smaller, right? But orthographic projection, there's no such kind of concept. All the things are projected to the same size in the image space, and we can make it much mathematically easier. And some specific example that we can approximate real perspective projection to orthographic projection is capturing some object with really small field of view. Field of view means like if we have camera, let's say this is camera, and this is field of view. If we have some capturing mode in mobile phone already. Wide angle mode, we have wide angle mode, right? To capture more object, we use wide angle mode. That means field of view becomes larger and larger. Field of view becomes larger and larger. If field of view is very small, like 0.05 degree, that is for capturing really big and really distant object, like capturing moon, capturing some Mars, capturing Venus. We need to make field of view very small and small and small, and object is really far from our Earth. And in this specific situation, we can approximate perspective projection to orthographic projection, and then mathematical stuff becomes much easier. But all the usual cases, like capturing selfie, capturing food, capturing any scene in our real world, most of the capturing is based on perspective projection. If object becomes farther and farther from camera, it becomes smaller and smaller. And there's as you can see, this is real 3D shape, but after you capture this, it becomes really distorted. And that is actually also related with the vanishing point. All the distance discrepancy between 2D and 3D is from perspective projection. We studied this a couple of times, right? Perspective projection can change parallel, do not preserve parallel, right? So all this kind of distortion comes from perspective projection. But that is what is happening when our eyes see the world, when our game engine renders real 3D world to our monitor, where some state-of-the-art physics engine renders some images to the to the movie screen. All this stuff are based on perspective projection. And this shows some difference between what is happening in 3D and what is happening in 2D. This is perspective projection. weak perspective projection and orthographic. And as you can see, if you just see at glance, I mean, increasing focal length or distance from camera. So increasing focal length means zooming. I mean, focal length is, we will study focal length, but you can understand this as a zooming in camera. That means zoom camera, it is different from zooming in 2D space. That is difference. So when you increase focal length, when you capture images, or images from here, you can know that there is no such kind of castle. There is no castle, just the sky, as you can see here. There were no castle. But then after increasing focal length, suddenly this castle appears. It's really strange, right? If we simply zoom images in a 2D space, this will not happen. It's just all the things will, remain the same, and just the size of this patch will increase if we zooming into this space. But in 3D space, as I said, it's different from simply zooming in the 2D space. Increasing focal length or increasing distance from camera, because of the perspective projection. If it is orthographic projection, then it is exactly the same. If it is based on orthographic projection, then simply zooming into this space or increasing focal length result in the same result. But our word, our projection, our eyes, our rendering engine, all the stuff are based on perspective projection, so that simply zooming in the 2D space is totally different from increasing focal length or distance from camera. So this shows some interesting visualization. And weak perspective projection is somewhere between perspective and orthographic. Perspective is like a real stuff that is happening in our real world, and orthographic is just a very simplified version of projection. All the 3D object is projected with the same size regardless of their distance from camera. But a weak perspective is like it could happen if object is very far from camera. Very far from camera, then let's say this is camera. Sorry for bad drawing. So this is camera, z-axis, and if this is object, this is camera. Cam object. If distance between this one, CO, and this is, let's say this is this is C cam, C OBJ. The size of the object is much smaller than distance between camera and object, then we can consider this as a single point, right? We can approximate this as a single point. If distance between camera and object is much larger than size of the object, then we can treat this as a single object. So the impact of perspective projection becomes very small. In the specific case, we can call this a weak perspective. That is somewhere between perspective and orthographic projection. And this shows description of orthographic projection. As I said, in original space, if object becomes farther and farther from camera, the projected image size should be smaller and smaller, right? But orthographic projection, from its name, we can know that this is not happening. Regardless of the distance between camera and object, the projected size of the object is the same. Where, if XC is here, XC is here, XC is here, it always projected to XS, the same position. So here, XS is equal to XC. That is orthographic projection. An orthographic projection of a 3D point XC depicts the coordinate XS. And the x and y axis of the camera and image coordinate system are shared. Light rays are parallel to the z coordinate of the camera coordinate system. And during projection, the z coordinate is dropped, and x and y remain the same here. And remark, the y coordinate is not shown here for clarity, but behaves similarly. It's it is the most simplest, easy to understand, intuitive projection. Just the real 3D object shape is just projected to the image space at the same size, regardless of their distance between camera and object. So mathematically, an orthographic projection simply drops z component of the 3D point in camera coordinate xc to obtain the corresponding 2D point on the image plane. And orthography is exact for telecentric lens, and as I said, telecentric lens is kind of capturing some very far distant stuff like a moon, Mars, Venus, capturing such kind of stuff. An approximation for telephoto lenses. After projection, the distance of the 3D point from the image can be recovered. This is definitely true, right? If we drop Z components, there's no way. I mean, the original one is XC, YC, ZC. Then it becomes XS, YS. So from its XS and YS, there is no way to recover ZC. There's no way to recover, right? That is definitely true. But unfortunately, orthographic projection itself does not actually make sense much because basically the unit is different. So, I mean, if we use like a meter, this might be about 0.1 meter maybe. Then 0.1, the number is, I mean, it's just used as 0.1 pixel. That is not the case, right? I mean, this maybe depending on the resolution of monitor, but this might take more than 100 pixels. But if we use meter unit, then this 0.1 meter unit is projected to the pixel unit without any modification. Then it might take 0.1 pixel, which does not make sense. So that what people often use when people try to use scaled orthographic projection is adding scaled orthographic projection. In practice, word coordinate, which may measure dimensions in meter, must be scaled to fit onto image sensor measuring in pixel. Because of course there is some difference between meter and pixel, depending on the resolution of monitor, depending on many things. But we do not expect this one take only 0.1 pixel. 0.1 pixel means, in image coordinate system, it is discretized to integer. Then 0.1 pixel is a 0 pixel. So we can't see this object in image if we use orthographic projection. That does not make sense. So that we need to introduce additional scale to change this any meter or centimeter, millimeter stuff to the pixel unit. That is called scaled orthography or scaled orthographic projection. Just simply, so in previous one, we just used 1, 1. That is the orthographic projection transformation matrix. But instead of using 1, 1, we just introduce scale S, where S can be predefined beforehand or can be optimized, anything you can choose. So the unit for S is a pixel per meter or pixel per millimeter to convert metric 30 point into pixels. And under orthography, structure and motion can be estimated simultaneously using the factorization method, the singular value decomposition. So what I want to try to say is that orthographic projection, although it's very simple, is too simple. It is also too simple, but this is too simple. So that, the meter unit just simply changed to pixel, which does not make sense. So we introduce very minimal stuff. We introduce very minimal stuff to make it work in real world applications by introducing scale, so that we can change change unit of the real world, meter to pixels. And now we have perspective projection. As you can see, this seems much more complicated than orthographic projection, right? So orthographic projection, no matter the distance, regardless of distance between camera and object, XC is always XS. But now it is totally different. As XS becomes, the distance becomes longer and longer from camera, the size of the object is different. And so the perspective projection of a 3D point XC to pixel coordinate, and we can use triangle similarity. The light, let's see this one first. Light ray passes through the camera center. This is camera center. And this is XC, C is camera coordinate system. This is in 3D space, and camera coordinate system, real object. And there should be light source, there is sun, and light hit this object, and reflected light comes to camera center. And light ray passes through the camera center here, pixel S and the point XC. So in the physical camera model, the axis should be at here, but we are now using mathematical camera model, so the axis is at here. Convention, principal axis, orthogonal to image plane, aligns with the z-axis. So convention is that there can be many variants, but the convention is that the orthogonal to image plane align with the z-axis. That is, we can use this y-axis or x-axis, but convention is that we use this one as z-axis. And this one is x, and here maybe y coordinate. It only shows x and z, relationship between x and z, but the y coordinate will behave similarly. And the important thing is that we use triangle similarity. So this is focal length, f here, f, and xs here, xs is here. So there are two triangles, the smaller and larger one. So the focal length and xs here, and zc, here is cc. This is here gc is here, zc and xc. From its triangle similarity, we can, and then we can now xs is f, cc, xc. So this is really different from orthographic projection. So f is focal length. This is a constant, and it can be considered as scale of orthographic projection. So we already introduced scale orthographic projection, right? So the f is scalar, so that it might be similar with the scale orthographic projection. But the important thing is that we divide xc with zc. This becomes really different. So the position of the point in the image coordinate system is related with the zc, depth coordinate of the 3D space. That is really different. So that is also consistent with visualization. In orthographic projection, regardless of the distance between object and camera, xc is always projected to xs, right? But now the projected position in the image coordinate system is related with the distance between camera and object. That makes really different things. In perspective projection, 3D points in camera coordinates are mapped to the image plane by dividing them by their z component and multiplying with focal points. So this is what I derived in previous slide, right? In mathematical form, in matrix form, we can rewrite this like this. And note that this projection is linear when using homogeneous coordinates. After the projection, is not possible to recover distance of the 3D point from the image. That is definitely true, right? From only xs and ys, we cannot recover zc because there's no clue to recover zc. And f, the focal length, is a pixel to convert metric 3D point to pixels. So, this one is meter, and meter is cancelled, and f should be pixel, so that it can be pixel. So f is, as I said, just some scale of orthographic projection. But the important thing is that, for example, if xs is xc, if this is the case, then this is exactly the same as the scale orthographic projection. But the important thing is that we have additional thing, this one, by dividing zc, the position of the projected point is dependent on the z-axis of the point in the 3D space. That is huge difference between orthographic projection and perspective projection. And this just some not very important. Just we introduced some point offset in 2D space. So without this, the image center becomes origin. But in convention, we introduce principal point offset to make the image about top left. Top left is 0.0. So this one becomes 0.0, and this one becomes height -1 and width -1. This is convention. So before this, introducing this offset, the center of image becomes origin, but what people mostly use is this convention, just making top left of the image 0.0 and the right bottom height -1 and width -1. Just introducing offset. And now we have some complicated things. So let's see this one. The complete perspective projection model is given by like this. So in previous example, we have only focal length and 1, right? But now, first one, we are going to introduce offset C, and second one, we can introduce scale as well. The left 3x3 submatrix of projection matrix is called calibration matrix. This one is called calibration matrix. When we only use focal length is the minimum component, necessary minimum component, and these are focal lengths, and we are going to introduce Cx and Cy to make image origin to the top left. That is the reason why I introduce Cx and Cy. And S is scale. Scale is usually 1, but we can use different scales. The parameter of K are called camera intrinsic. This is very important. Intrinsic means we have in, right? In means some internal stuff. That means controlled by camera, controlled inside of camera. We can change focal length, we can change scale, we can change this Cx and Cy, principal offset, inside of camera. There are some options if you got some camera, you have some options to adjust focal length or scale or such kind of stuff inside of the camera. So you can control anything. We can control anything about camera intrinsics. And that is the reason why we call this matrix, 3x3 submatrix, as camera intrinsic matrix, calibration matrix. This is different from extrinsic parameter. We will study this later. So this is a very generalized form, fx, fy, cx, cy as very generalized form. Here fx and fy are independent only for different pixel aspect ratio. But usually, in real world, usually fx and fy are the same. Scale is equal to 0. C is just the center of image. This is really generalized form of camera intrinsic matrix or calibration matrix. But in real world, we often set focal length the same because we want to preserve aspect ratio between x and y axis. So that is the reason why I often set fx and fy the same. Scale just 0, and C just the center of object, center of image. So in real world, this is very generalized form, but in real world, f0 with -2 f. This is what people usually use. Sorry. This is what people usually use. So fx and fy are the same. Scale is just 0. And principal point, cx and cy are just center of image. Width divided by 2, height divided by 2, 0, 0, 1. This is often called K. Calibration matrix, camera intrinsic matrix. As I said, intrinsic means from its name, we can know that there's an in, right? So there are two matrices, intrinsic matrix and extrinsic matrix, only two matrices. Intrinsic matrix, as we can learn from its name, know from its name, we can control these parameters inside of camera, focal length, skew, or some principal point offset. We can control such kind of stuff inside of camera. But on the other hand, extrinsic means we cannot control this inside of camera. That means we will study this later, but this is out of control of camera. This is relationship between different cameras. So anyway, this is often called calibration matrix, intrinsic matrix. And this is extrinsic matrix, chaining transformation. So let K be the calibration matrix, intrinsic, and RT the camera pose. So the definition of pose is a combination of rotation and translation. So the So let's recap this one. The reason why we introduced calibration metrics is that we can control focal length. Focal length is about zooming. Focal length, zoom. We can zoom. We can take a zoom when capturing images, right? So that is the reason why we introduced camera intrinsic metrics. But extrinsic, why we are going to introduce additional extrinsic metrics is so difficult. So the reason is that there can be multiple cameras or moving camera. I mean, inside of camera, if our coordinate system is just seeing only a single camera and just looking the screen with respect to the camera pose, then there's no reason why we introduce extrinsic camera. But there can be, for example, if we can use two cameras to capture an object, right? Then there should be some relationship between these two cameras. How these cameras are rotated with respect to each other. I mean, distance between these two cameras, translation vector between these two cameras. So that is the reason why we introduced extrinsic camera metrics. So the relationship between, it tries to deliver a relationship between two cameras. And formally, so to define extrinsic camera metrics, we introduced word coordinate system. So this is I know it's very confusing, very complicated, but there are three coordinate systems. Now is the end. Don't be afraid. There are three coordinate systems. First one is word coordinate system. Actually, I made a slide to, yeah, you can, I guess this would be better. So word coordinate system is just a reference coordinate system. It does not change. No matter where you're looking at, no matter where camera is, it just remains the same. Always fixed at the some points like here. X, Y, Z is the same. Always fixed word coordinate system or reference coordinate system. And camera coordinate system, as you can see, orange one. There can be some object in word coordinate system, then you might want to take picture of this image object from maybe different cameras or some moving cameras. So there can be various combination of rotation and translation of cameras when capturing images of an object or anything. So that here is a camera coordinate system. Camera coordinate system means, camera is always centered. Camera relative coordinate system. Camera relative coordinate system. This one is always x-axis of the camera coordinate system, y, z. And if you rotate camera, it doesn't matter. Just always fixed. Respect to camera pose. That is camera coordinate system. And then image coordinate system that we can see we see through our eyes, or through our monitor screen. All the things are image coordinate system. But there are three coordinate systems. And to convert word to camera, we need extrinsic. And to convert camera to image, we need intrinsic. Right? To change a reference coordinate system, which is called word coordinate system, there can be multiple cameras. We can change this word coordinate system to coordinate system of each camera. That is, to do this, we need extrinsic camera parameter. And once we got camera coordinate system, then we need to project them to image space so that we can see it. That is about intrinsic camera parameter. That is the reason why we introduced this kind of complicated intrinsic, extrinsic pose, rotation, translation, all that stuff. I think this will be easier. So then let's see this one first. Extrinsic. Sorry for changing the order. So intrinsic, as I said, is about word to camera coordinate system. This is slide 48. Word coordinate system to camera coordinate system. And here R and T represent rotation and translation respectively. So rotation with respect to word coordinate system. So this is word coordinate system, and this one is this one camera coordinate system, then there should be rotation. This is always fixed. World coordinate system is always fixed. And camera coordinate system, we change rotation, translation, whatever, then there can be always relationship between world coordinate system and camera coordinate system. That is about R and T. We use applied rotation to convert this world coordinate system to camera coordinate system. But then we need to change position as well. If we only change rotation, then the position will be the same. But then we need to change translation so that rotation is 3x3 rotation matrix, and translation is just a three-dimensional vector. And then multiply with 3D homogeneous coordinate in world coordinate system, and output 3D Euclidean coordinates, right? So W represent world and C represent camera. That is the role of extrinsic camera matrix, which is combination of R and T. So this is, as I said, 3x4 matrix, because R is 3x3, and this is 1x3. No, 3x1. So that we have a 3x4 matrix. But in computer graphics, especially if you're using OpenGL, or actually in anything, we often convert it to, we pad RT with the 0001 row vector at the last row to make it 4x4 matrix. It's mathematically more convenient. This is for convenience, but representation is just the equivalent, the same. The important thing is that extrinsic matrix, which is a combination of rotation and translation, is to change some constant reference world coordinate system to moving cameras, some multiple cameras, any cameras. We'd like to change this world coordinate system to camera relative coordinate system, so that we can define coordinate system for each camera, for each time step if we move cameras. It's good? Okay? And now remaining, so this was extrinsic. X means external. As I said, extrinsic matrix is not controllable inside of camera. Position, rotation is not controllable inside of camera, right? That is why we call this extrinsic matrix. And intrinsic, from its name, we can know that we can control intrinsic matrix, parameters in intrinsic matrix inside of camera. We can change focal length, we can change skew factor, such kind of stuff. And the K, the calibration matrix or intrinsic matrix that I introduced in the previous slide, is to change camera coordinate system to image coordinate system. By applying extrinsic parameters, we change world coordinate system to camera coordinate system. From its camera coordinate system, now image space is what we finally need, right? To see something into this space. So that we need to use intrinsic matrix. In general, it's 3x3 matrix. There are two options. The first one is multiply with 3D Euclidean coordinates. This is from this one, right? It's extrinsic changes world coordinate system. 3D homogeneous coordinate to 3D Euclidean coordinate. And then it takes 3D Euclidean coordinates and outputs 2D homogeneous coordinate, UVW. And now, or the second option is multiply with 2D homogeneous coordinates, already divide with Z, so that the last element is just 1. So that it is 2D homogeneous coordinates. And outputs 2D homogeneous coordinates, U divided by W, V divided by W, 1. And here is the important thing. This is where distortion is happening. Vanishing point or some discrepancy between 3D and 2D. All this stuff is happening in here because we divide coordinate with depth Z. So that in extrinsic matrix, there's nothing special, just a 3D translation, 3D rotation, that's all. There's no distortion, very clear. There's no dimension reduction, just 3D to 3D. But in intrinsic matrix, now we are going to project 3D data to 2D space, and that is where distortion is happening. Vanishing point or anything like this kind of distortion. Where is it? This kind of thing. Any discrepancy between 3D and 2D is happening in here by applying intrinsic matrix. And this is where perspective orthogonal projection is applied as well. Perspective orthographic. Anything projection is happening. Right? We learned the geometric transformation, homography, projective metrics, such kind of stuff, or more formally, perspective projection, orthographic projection is happening in this intrinsic matrix. And as in particular, perspective projection if perspective projection is applied in this intrinsic matrix. And by design, if intrinsic matrix is focal 0, CX, 0, focal, no, 0, 0, CY, 0, 0, 0, 1. If K is like this, then that is saying we are going to introduce perspective projection. Then distortion is happening. Any discrepancy between 3D and 2D is happening. But if we design K just a this kind of orthographic matrix, there can be multiple K's. If we design K like this, then that is saying we are going to use orthographic projection, so there is no distortion. And in computer graphics, OpenGL, actually anything, we pad K with 0, 0, 0, 1 row column vectors. So originally it was 3 by 3 matrix, but we pad 0, 0, 0, 1 to the last row and column so that we make them 4 by 4 matrix. Just some convention. Mathematically, just equivalent. There's no difference. So what I want you to guys is understanding relationship between these 3 coordinate system: world coordinate system, camera coordinate system, and image coordinate system. Why they are necessary, and how can we convert world coordinate system to camera coordinate system? We use extrinsic camera parameter to change world coordinate system to camera coordinate system, and restoring back to world coordinate system is also possible because there is no information loss. We applied world to cam is just a xc is r x w doggy t plus t. Sorry. And then we want to change world coordinates. No. And then we might want to restore camera coordinate system to world coordinate system. We can just invert it. Then xw is xc minus t r inverse, right? There's no information loss. We can change word to cam or cam to word. If we have extrinsic camera parameter, there's no ambiguity. Just the 3D rotation, 3D translation, that's all. But this is different. This is extrinsic. Intrinsic, we project 3D to 2D space so that we lose z coordinate. Then in theory, there's no way to recover camera coordinates from image coordinates. In theory, there's no way. Because we only have x and y. Let's say we have image of this remote controller, then we can't know the distance between this button and my eye. There's no way. Right? So there is an information loss, and let's see it mathematically as well. So camera coordinate is screen is focal dot. Okay, right? C is camera, S means screen. If we know XC and ZC, then we can change it to screen space. There's no ambiguity. But what if we want to recover camera coordinate from screen space? How can we do that? we need depth. We need depth of the point in camera coordinate system. But when projecting, we already dropped this. So there's no way, in theory, to recover accurate X position in camera coordinate system unless we know exact depth. And that makes computer vision really difficult. From image, we lost depth. When capturing image from real 3D world, we lost Z component. There's no way, in theory, to recover actual 3D coordinate system, 3D world coordinate system. But to understand what is happening in our real world, we need to get to know what exact 3D shape of the object, shape of the scene, shape of the world. But in theory, there's no way to recover such kind of accurate 3D representation because we have limited information. We already dropped Z coordinate when capturing image. That makes computer vision really difficult. We do not have 3D information. So before deep learning is invented, there was actually no reliable solution for single image to 3D reconstruction. Because as you can see in theory, without Z, there's no way to recover XC, right? But after deep learning is invented, we can train some neural network to take 2D information and output 3D information. A very magical tool. Without ZC, the model learns some plottable distribution of ZC, so that from only single image, it can output some reliable 3D representation by providing massive amount of training data. So after deep learning is invented, lots of single image-based 3D stuff is invented. And the reason why that is surprising is that theoretically it's impossible. But in some magical tool approximation, many stuff, now we can do that. Okay, let's finish today and check the attendance and finalize. You can put 4, 8, 5, 4, and then leave this place. Thank you.